nice introduction. It is a great pleasure to participate in this workshop. And I would like to thank Daniel and Kavita for the invitation. So my talk is based on working with various people. One of them is Yatin Shao. Another person work was with Adrien Tudorescu. Then I am also going to talk about some result I obtained with Alpa Mezaros, Tenchen Mu, and John Fengstein. Okay, so I would like to emphasize the geometry aspect of the common noise operator. I would like to argue on the limitation of the common noise in improving regularity. And the above justify the need to impose a monotonicity condition if one wants to maintain regularity. I will comment on a new type of monotonicity condition, which our work with Mezaros, Mu, and Zhang is based on. So let me start with a Hilbert approach as done by Pierre in his talk. So I am going to choose O to be the unit cube in RD, and I will choose my probability measure to be the Lebesgue measure restricted to the cube. In fact, I could replace O and P by any non-atomic probability space for what I want to do. Then I will introduce the Hilbert space of vector field from O to RD, such that the square integral with respect to Lebesgue measure is finite. This directs us to consider the flat manifold M, which is RD by the Hilbert space. So I would like to recall that if I have a function, a real value function defined on M, it is twice differentiable at a point M if there exists a Zm in M, and there exists a bilinear symmetric bounded form such that I can write a second order Taylor expansion. So my second order Taylor expansion will have a linear term in H, a quadratic term in H, and a little o term in H squared. Em is the gradient of U hat at M, and the bilinear form is the Hessian of U hat. So next, I choose any orthonormal basis in RD, and I am going to identify each element of the orthonormal basis with a constant vector field. So I am going to form a vector capital I. The first component will be an element of RD. The second component will be my vector field. So that belongs to the tangent space at M. And since I am on the flat space, the tangent space is independent of M. Call E the finite dimensional space spanned by the vector field E1 to ED. This forms an orthonormal family with respect to the natural inner product. And as you can see, the dimension of E is D. The dimension of the tangent space is plus infinity. So we define the partial trace of the Hessian at M by computing this bilinear form by looking at the restriction of the bilinear form to the tangent space. Since our manifold is a flat space, you can write this partial Laplacian directly as the second derivative along a specific path whose direction are given by the tangent vector EI. So as you saw, this partial Laplacian take into account only D direction in a tangent space which has infinitely many directions. Therefore, you cannot expect the partial Laplacian to have a smoothing effect because you are missing too many directions. For instance, if you look at a very simple equation, I start with a value function on my manifold, and I want to study the analog of the heat equation with an initial condition which is given by U0. You cannot expect this equation if you start with U0 in a certain class. You cannot expect this solution, this equation to improve the solution, regularity of the solution over time. Even worse, use a Hamiltonian, which is defined on the manifold cross Rd with value in R, and introduce a terminal value function G hat, which is defined on my manifold. So I am going to play with an intensity which is non-negative. This intensity will allow me to make the partial Laplacian appear or make it disappear from the equation when beta equal to 0. It is hopeless to expect a general regularity theory for this type of equation. So the equation, I chose precisely this equation because this is what corresponds to the master equation in Hilbert setting when I am dealing only with a common noise. No individual noise appear here, and we will see very soon why I say nothing about individual noise in the Hilbert space setting. So our lock in a mean field game is we are not considering arbitrary U hat. We are considering U hat which are rearrangement invariant. So what I mean is if X and Y have the same law, then U hat applied to X has the same law as U hat applied to Y. Let us denote by P2 of Rd the set of probability measure on Rd which have a finite second moment. So I am going to define a function on the set of probability measure using my U hat. Since U hat is rearrangement invariant, this definition is consistent. So U of Q mu is U hat of QX, where X is any random variable whose law is mu. There is a result due to myself and to the rescue, which says that if U hat is rearrangement invariant, if you take any element of minimal norm of the subdifferential, so the subdifferential of U hat will be a convex set, a closed convex set. Therefore, by standard convex analysis theory, it has an element of minimal norm. If you take the element of minimal norm to be Z zeta, then you can factorize zeta through a vector field from Rd to Rd. Z psi belongs to the intrinsic subdifferential of U at Q mu. So here, I am not pretending I have defined, I have told you what the intrinsic subdifferential is. If you don't know what it is, take this as the definition. If you are familiar with the theory of Ambrosio, Gigli, and Savary, I am saying that the subdifferential defined intrinsically by Ambrosio, Gigli, and Savary coincide with the subdifferential obtained here by factorizing my vector field. The corollary of that is if U hat is differentiable at M, then the subdifferential has a unique element in the tangent space. And so Z must be the gradient with respect to Q of U, and psi is the Wasserstein gradient of U with respect to mu. And you can take this as a definition if you don't know the intrinsic versus time gradient. But if you know it, this becomes a theorem where I am saying that psi coincide with the intrinsic versus time gradient. Similarly, when you look at second order differential operator, they get factorized. So the Hessian of U, which I wrote on the tangent space, it is going to factorize into objects which depend only on Q and mu. And I have written there the list of objects. So when you write your Taylor, second order Taylor expansion in the Hilbert space, you see a second Taylor expansion appear on the versus time space. And from the second Taylor expansion, you can identify the object I have there. The argument, for instance, the first object, partial derivative QQ of U, and the second object, partial derivative Q tilde of U, they don't have the same argument. And so I have to use the appropriate argument. One concluded that the Laplacian on the versus time space can be obtained to a factorization procedure. So you look at the partial Hessian on the finite dimension of space, and it gives you a partial Laplacian on the versus time space. For the moment, you can take this as a definition and say you obtain the factorization of the Hilbert Hessian, and the object you obtain, you call it the versus time Laplacian. So when you look at the expression which appear in your computation. So I am not showing the computation here. I am taking for granted that I have made the computation before, and I am collecting what I get. You are going to see two categories of term. I group the term into two parts. The first one is the Laplacian of U with respect to Q. And the second one is the trace with respect to Q tilde of mu, the trace of the second derivative of. It turned out that this first part is the individual noise operator. And you have a second part which appears. I am going to comment on it later. So when you write the versus time Laplacian, inside it, the individual noise operator appears. For instance, when you look at what I call O, the individual noise operator, when you look at it, you look at its restriction to a particular class of function. You search for the eigenvalue of this operator. You can show that the eigenvalue are straightly negative. However, if you look at the eigenvalue of the whole thing, the eigenvalue are non-positive, but they can be 0. O is a uniformly elliptic operator, and the partial Laplacian is a degenerate operator. I am not going to say more about this here because I will need to do some computation. Will need to compute the Laplacian of the object, which are the function which are here, and I don't want to do that. So when you consider the initial value problem, you take the partial Laplacian, you add epsilon O to it, and assume that your initial condition belong to this special class. You improve regularity when epsilon is strictly greater than 0. So what appears here on the slide is false. I am supposed to write epsilon strictly greater than 0. And you maintain the same level of regularity when epsilon equal to 0. So O has a smoothing effect. It improves regularity, whereas the partial Laplacian maintain regularity. So if you want to understand why the partial Laplacian doesn't improve at all regularity, you look at, for instance, the harmonic function. You solve the equation Laplacian of u equal to 0. You look at this harmonic function and you see that they have no regularity property. In conclusion, we have the common noise is the individual noise plus an over operator. The individual noise improves regularity. The common noise maintains regularity. This means that the second part, which appears in the common noise in an operator, which destroys regularity. And you can see that clearly if you do a Fourier analysis in the class of initial value function I wrote earlier. So I would like to warn you that when I was deriving the partial Laplacian on the Wasserstein space, I was able to get it from an operator in the Hilbert setting. So I can go from the Hilbert setting to the Wasserstein space and go from the Wasserstein space to the Hilbert setting. However, when I separate the partial Laplacian into two operators, one of them being O, we don't know how to leave O to the Hilbert setting. The fact that we don't know how to leave O to the Hilbert setting make it difficult to connect, to use a finite particle approximation in equation which depend only on O. So when you have an equation depending on the partial Laplacian, you can use a finite particle technique, study the evolution of finitely many particles, pass to the limit, and obtain at the limit the continuum equation. However, when you have only the O, which is the individual noise operator, there is no Hilbert analog we are aware of, and so this makes the strategy of finite particle difficult to apply. So from now on, I am going to assume that I have a Hamiltonian defined on the Cartesian product of three spaces. The set 1 RD represents the set of position. The second one, the set of probability measure on RD, represents the distribution of the player. And the last set RD represents the momentum of an individual player. I am going to assume that I am giving a value function which is given on a Cartesian product. The first one represents the position of a player, and the second set represents the distribution for all the players. I can leave H to the Hilbert space setting by saying that H hat of S is H of the law of X. And I can do the same thing. I can leave the terminal value function to the Hilbert setting. And so I am again in situation where I can differentiate H hat, I can differentiate G hat, and relate the differential to the differential of H and G. The master equation with both common noise and individual noise is you compute the derivative of u with respect to time, you subtract the Hamiltonian. Then you add a second order operator, which depend on two parameters, beta naught and beta 1. So I put beta naught in front of the partial Laplacian. I put beta 1 square in front of the individual noise operator. And you have a non-local term which appear as a correction when you are computing direction derivative of a function which depend on u a part sigma t. And the terminal condition is G. When beta 1 is not 0, we are not able to leave since we are not able to leave the individual noise operator to the Hilbert setting, I will not be able to write a general Hilbert space setting for the master equation unless beta 1 equal to 0. Our study, as everybody does, will be on the set of in order to solve the master equation and have a long-time existence result, one needs to impose some monotonicity condition. There are so far two types of monotonicity condition I am aware of. The first one is due to Pierre-Louis-Lion, Lasry and Lion. And if you are familiar with one Wasserstein metric, so this is the Wasserstein metric where the cost function, the cost for transporting a unit mass from X to Y is the distance from S to Y. The Wasserstein one metric has many geodesics, infinitely many geodesics. One of the geodesics is given by this classical interpolation between the measure mu0 and mu1. And the Lasry-Lion monotonicity condition is a monotonicity condition with respect where you are traveling along this Wasserstein 1 geodesic. This condition is amenable to state for separable Lagrangian, which means Lagrangian, which can be written as a function of QV, separated with a function of Q mu. One can try to write a Lasry-Lion monotonicity condition for general Lagrangian, which are non-separable. So you just try to write the condition, which will ensure that if you start with a Lasry-Lion monotone terminal value, what condition on L will guarantee that the solution you construct, the solution of the master equation you construct at a later time will also satisfy the Lasry-Lion monotonicity condition. But the condition for general Lagrangian is cumbersome to state, and I am not going to try to touch it. I have not really tried to do an existence theory for a general version of the Lasry-Lion monotonicity condition. And I don't know which obstacle we may have to face. We propose another monotonicity condition, which we term a displacement monotonicity condition. It is derived by using the two Wasserstein geodesics. For instance, if you take two Dirac masses and you want to interpolate the two Dirac masses, the geodesic in the two Wasserstein space is obtained by interpolating the point and then applying the Dirac masses. More generally, you can express the geodesic, the two Wasserstein geodesic. It is equivalent to the geodesic on the flatter Hilbert space. So you lift your function to the flat Hilbert space, and you use the geodesic there. They correspond the displacement monotonicity condition on Hilbert space, on the Wasserstein space, will be a monotonicity condition on the Hilbert space. So I will start with a value function which depend only on the position and the distribution. Displacement monotone if data inequality is true. So you take any mu and nu probability measure of finite second moment. You take any gamma, which has a mu1 and mu2 as marginals. And you integrate that expression with respect to gamma. It has to be non-negative. For smooth displacement, for smooth function, so by smooth, I mean instead of imposing a condition on knowing that the first derivative of G exists, assume I know the second derivative of G exists. Then the previous condition I wrote, one can show that it is equivalent to showing that a quadratic form defined on the tangent space is non-negative. So this quadratic form involves the derivative of G, the mixed derivative with respect to Q mu, and the derivative with respect to Q. You can see that in the previous expression I wrote, although it looked like the last term is integrative with respect to Q tilde, in fact, it is not. You can make this integral disappear. It has no effect on the second term. So you conclude that the two expressions in the integral scale differently. So you replace the mu by a convolution. And so you replace mu by rho epsilon convolution mu. And you let epsilon go to 0. One of the expressions is going to disappear, and you will be left with the conclusion that the Hessian of G with respect to Q is non-negative. So from the Hamilton-Jacobi point of view, this is a tremendous help in the study of regularity. So when you are studying Hamilton-Jacobi equation, you expect the value function to be semi-concave. If you are given for free that the value function are convex, you get immediately that G is locally Lipschitz. In contrast, the Lasry-Lions monotonicity condition, it removes from the expression I wrote for the displacement monotonicity condition, it removes the partial derivative with respect to QQ. It keeps only the first term, and it imposes that this first term is non-negative. There are plenty of examples showing that Lasry-Lions monotonicity doesn't imply displacement monotonicity, and vice versa. For instance, if you take a function of class C2, which is symmetric, and assume that the function grows at most quadratically at infinity, when you look at this convolution, it is Lasry-Lions monotone if and only if the Fourier transform of phi is negative. For instance, phi of s equal to negative s squared is the one which has a negative Fourier transform. And so in this case, this function is Lasry-Lions monotone. However, if you want the same function to be displacement monotone, you have to impose that phi is convex. And so in the case above, I have to replace negative s squared by the norm of s squared. We need to extend the notion of displacement monotonicity to functions which are defined, which depend on 3 variables. So the position, the distribution, and the momentum. In the sequel, I am going to impose that there exists a positive constant such that the second gradient of h with respect to the momentum variable is bounded by the inverse of c. And I impose this growth condition on the gradient of h with respect to q. So displacement monotonicity condition can be defined solely in terms of h without involving a Lagrangian. But to keep the definition consistent with the one of function which depend only on the variable q and mu, I opt here for a definition or displacement monotonicity definition for Lagrangian. So I am going to say that H is displacement monotone if L is displacement monotone, provided that H comes from a Lagrangian L is the Legendre transform of a Lagrangian L, where I make a correction negative in the Legendre transform. So I am assuming that my L, the Hessian of L, is strictly positive in the velocity variable. Displacement monotonicity means that one quadratic form depending on L is greater than another quadratic form depending on L. So if you look at the first quadratic form, it is exactly the same quadratic form I wrote for G when I have only two variables. But since L depends on a third variable, I have to write the velocity in terms of x. The second expression is new. The second quadratic form is new in the sense that I have not written it before earlier in this talk. What I call A is an argument where the velocity is replaced by a function which depends on x. And the phi is chosen to be of class W1 infinity just to serve as a cutoff function so that we don't worry about what happened when the momentum becomes large. So I think I thought it is good to make a clarification on what I mean by continuous differentiability on the Wasserstein space. So if I go back to the beginning of my talk, I define the Wasserstein gradient from the Hilbert gradient. Now, this means that my Wasserstein gradient is defined on the support of x. It is defined on the range of x, which means the support of mu. As a consequence, the Wasserstein gradient is defined only on the union of the set I wrote below, not everywhere. So we say that G is continuously differentiable if the Wasserstein gradient, which is defined on this small set, has a continuous extension on the whole bigger set. This extension can sometimes be unique. In particular, in the study we carry here, these extensions are unique. A way to guarantee that this extension exists and is unique is, for instance, assume that the Wasserstein gradient is a Lipschitz with respect to the three variables, Q, mu, and Q tilde. If I take a measure mu1 and a measure mu2, which is absolutely continuous with respect to Lebesgue measure, with positive density, then the support of this measure is the whole RD. And so the Wasserstein gradient is defined on the whole set RD. If I have this uniform control, Lipschitz control, then there is a unique way to extend my Wasserstein gradient to the whole space. Inductively, we are going to define the higher order differential function. So to study the master equation, I am going to assume that the derivative of G up to the third order are uniformly bounded. The derivative of H up to the third order are uniformly bounded on the set below. So depending on which derivative of H I am talking about, the argument, it may have three arguments or it may have two arguments. And I am imposing that I have a uniform bound, except that in the P variable, the moment variable, the bound will be only local. Result which we rely on existence of solution to the master equation for sufficiently small time is something which is by now well understood and can be found in the book by Carmona and Delary, when the time is sufficiently smooth and no monotonicity condition is required here. Our study consists of a series of results where we want to extend the above result to arbitrary time. This will come with a cost. The cost will be that we'll have to impose a structural condition on the data. And our structural condition here is the monotonicity condition. In a work with Mészáros, Moore, and Zhang, we assume that beta 1 is greater than 0. G and H are displacement monotone. We show that if U is a classical solution to the master equation, if we have a control on the derivative of U at a positive time, U is a displacement monotone. So the strategy in the proof is the following. The strategy doesn't need beta is greater than 0. You assume that G and H are displacement monotone. You look at the expression, the bilinear form, which characterizes displacement monotonicity for value function. So we are able to construct a path such that along that path, you have dissipation of displacement monotonicity. So I write my quadratic form in terms of U. I search for a part in the set of probability space, and I apply U to that path. I differentiate the bilinear form along that path, and I obtain an explicit expression, and that explicit expression contains the bilinear form which characterizes the displacement monotonicity of H. Therefore, it is enough to know that the displacement monotonicity bilinear form of G is non-negative to conclude that the one of U is non-negative. Another result we state in the same work. I am making assumptions stronger than assumption we made in that work because I am trying to be brief and not too technical. We can show that U and the gradient of U with respect to Q are uniformly Lipschitz continuous in mu under the W2 metric with a Lipschitz constant, which depend on expression involving only dt, the gradient of U with respect to Q, and the second gradient of U with respect to Q, and also constant which depend on G and the gradient of G. That is not enough for our whole study. We are going to deduce, we will need to deduce W1 Lipschitz property, which we do later. There is a well-known representation formula for what the solution of master equation is supposed to have. This representation formula have been adjusted in a few work, for instance, in a work by Moore and Zhang, and over for the derivative of U, the Wasserstein derivative of U, and over higher order derivative. So we check that this representation formula work in our case. And finally, we prove that if the terminal value function and the Hamiltonian are displacement monotone and sufficiently smooth, if we impose a suitable bound on the derivative of G and the derivative of H, then there is a unique classical solution to the master equation. And here, I forgot to write that beta 1 is greater than 0. So this statement I am making, the theorem 1 to 4 impose that the individual noise must be present. I would like to end with some comment on the case beta equal to 0. Beta equal to 0 is known to be within reach for potential mean field gain. Indeed, in a recent paper with Mezaros, assuming that L is separable and is derived from a potential, assuming that G is also derived from a potential, we are able to link the master equation to some Hamilton-Jacobi equation on the Wasserstein space. And we show that when beta naught equal to beta 1 equal to 0, then the master equation also has a classical solution. So this is the last statement of my talk. Thank you for listening. I went a little bit over time because I started a little.
Thank you. Are there any questions?
In your last slide on which is on the slide, theorem 5, there is a monotonicity condition which is floating around, right? You assume that the data is that F and G are monotone, right?
Yes.
So somehow
here
in theorem 5, the last theorem you quoted.
So in theorem 5, I am assuming that the potential is a displacement convex.
Okay, this is so that was my question. Thank you very much.
Yes, and also the potential which produces G is also displacement convex.
Any other questions? Any question online? So if not, let us thank Wilfrid again. Thank you, Wilfrid.
Thank you.